in K3 such that, so if I find P in there, I can assume that such that Q, let me call this one E1, right? Such that Q evaluated on E1 is 0. Right? This is exactly what it means to say that the point x to y to z is in the curve C. Yes? And so now Q is non-degenerate. So there exists a vector E2 in K3 such that, so let me call this non-degenerate bilinear form phi. Phi of E1, E2 not equal to 0. Right, and then I can multiply this one by a scalar if I want to. I can make this equal 1. Right, so then what I'm going to get is that phi has matrix like this, 0. So if I can do E2 maps to E2 plus E1, E2 plus some multiple of E1, this doesn't change this condition here, because I'm assuming that phi of E1 equals 0. So it doesn't change. I can do this as I like. On the other hand, I can arrange that phi of E2 is 0. Yes, because when you change the vector E2 by this, then you change this value in a linear way. Right? And so this means that if I've got a basis E1, E2, E3, a basis of K3, right, then I've already got this matrix. Right, because I've arranged that E1 is 0, I've arranged that E1, E2 is 1, and I've arranged that E2, E2 is 0. Right, so I'm sort of some way towards making a normal form for this matrix. So now choose E3 so I want to say E3 is orthogonal, is perpendicular to E1 and E2. Right? So I'm just saying phi of E1, E3 equals phi of E2, E3 equals 0. Right? I can do this because each of these conditions is one linear condition on a vector in this three-dimensional space. So I take this three-dimensional space and I impose these two conditions. Right? So I can arrange also that these guys are 0. Right? And furthermore, this guy is now not 0. Phi of E3 is not 0. Right? So now, there's still a problem of taking the square root of whatever this number is, which is why I say I'm allowed to multiply Q by a scalar. Right? I'm not interested in Q itself, but only in the condition Q equals 0. If I multiply Q by a non-zero scalar, it doesn't matter. Right? So after doing that, I can assume this one is a square. I can take the square root of it and put it inside the E3 there and arrange for this to be 1 or 2 or whatever I like. So I can arrange this one to be 1. And then I can mess around with E1, E2 to make this a half. Right? And I've finished. My quadratic form is like this. Okay? So that's this theorem. Okay, so when you do school maths, or maybe first year coordinate geometry, I don't know if it's done in universities or in schools, but you do something called conic sections, or conics, in K2. Well, you do, sorry, in R2. Right, and the ones you remember are the ellipse and the hyperbola and the still alive and the parabola. Right, and so you know, as you all remember from school, you do something like x squared over a squared plus y squared over b squared equals 1, and here you do you know, equivalent thing, x squared over a squared minus y squared over b squared equals 1, and here you do, for example, x equals lambda times y equals lambda times x squared, y equals c times x squared. Yes. So the point that I'm making is that each of those three guys is a non-degenerate, non-singular conic in R2, and there are three different ones of them. If you want to consider also the degenerate ones, you have line pairs and double lines, right? But if we were in projective space, the thing I've proved here is that there is only one. And so in R3, in R2, I have three different non-degenerate conics. So if you count the Euclidean metric and so on, there's also this notion of eccentricity. So if you already have a Euclidean metric on your space, then you really need to know the value of these a squared and b squared. You know, even a circle has a radius in Euclidean geometry. So up to, in the kind of geometry I'm doing, I'm not specially concerned. I can multiply the x and the y by scalars if I like. And so then I can say that this is just one curve, and this is just one curve. So three different non-degenerate conics in P2 R, or P2K. This is basically any field. There's only one. There's only one non-degenerate, non-empty conic, namely y squared, xz equals y squared. So I'm not explaining why I'm changing these coordinates around like this, but so, you know, my picture of P2 is this. Right, so this is x equals 0, and this is y equals 0, and this is z equals 0. And which is, what's my conic? So, the point 1, 0, 0 is in there, and also the point 0, 1, 0. Right, so where are they on the picture? I'm sorry, I apologize. Yes. So my conic is, if I draw the picture like of projective space like this, what I have, my conic is here. Right. It passes through these 2 points. So this is where y equals 0 and z equals 0. So this is the point 1, 0, 0, and this is the point where y and x are 0, so it's the point 0, 0, 1. Yes, and also at 1, 0, 0, the the line z equals 0 is the tangent line. So let's think about the procedure I was saying earlier. Suppose that I'm at a point where, suppose that z is not equal to 0. Right? So suppose I'm near this point. Suppose I'm standing sort of somewhere near here, where z is not 0. Then I have the xy plane and the curve x equals y squared. So this is a parabola. Yes, so if I was doing the same at the other point, then this is a place where x is not equal to 0, so I can set x equals 1 if I want to, and then I'm getting a different parabola, z equals y squared. If instead of doing this I do x, I can choose coordinates so that x and z are x primed plus or minus z prime. So if I do this, then this equation becomes x primed squared minus z primed squared equals y squared. Right? So there's a little change of coordinates. This guy here, this equation here, as I said, this is my favorite equation for the conic. Right? But I can easily make a change of coordinates and get a different one. Yeah, at least if in characteristic not equal to 2, this is an immediate coordinate change. In characteristic 2, you just have to do something slightly different. Yes? And then if I set, which one am I going to set equals 0? If I set x primed equals 0, I'm sorry, if I take this equation, I set x primed equals 1, I get the ellipse y squared plus z prime squared equals 1. Right, if I set z primed equals 1, I get a hyperbola. Right, so I have this picture there which you all remember from school days, and I have the picture over there which is, you know, in this slightly more abstract space. So what's going on here? Well, you know, what's the difference between these pictures? Well, you know, I mean, they are really pretty different, aren't they? They are really very substantially different, aren't they? I mean, they're all given by quadratic equations. That's one thing they have in common. But this one is bounded. This one is just a circle. It stays in a little part of the plane. This one has these 4 branches, 2 different lines going off to infinity, called asymptotic lines. And this one, well, you know, you don't really see the asymptotic lines. You can argue that the slope, as you go, as the x and the y get bigger and bigger, the slope gets higher and higher, and therefore this is asymptotic to this. But you know, that's just a. So what's happening? What's happening in this model is I have this once and for all defined favorite conic given by x z equals y squared, and let's throw away this line. Right, if I throw away the line z equals 0, then what I see is the ordinary parabola, the straightforward parabola. I'm seeing just x equals y squared. It's a change of permutation of the variables. If I set instead x to be one of these guys to be 0, so I set x to be equals z or z equals x, then I'm getting I'm doing something like this. I'm cutting like this and seeing an ellipse, or I'm cutting like this and seeing a hyperbola. And so what the projective space is doing for us here, it's unifying the 3 different families of conics over there into just one single construction. So what's the real difference between these? Well, this one doesn't have asymptotic lines to infinity at all. This one, in R2, it meets the line at infinity in two complex conjugate points, in 2 points that aren't real points at all. This one here obviously meets the line at infinity in two different directions. A line at infinity is as I said, if you want to think of the points at infinity inside the ordinary coordinate plane, you have to think of them as directions of pencils of parallel lines. So there's a direction here which is asymptotic, there's another direction which is asymptotic. Whereas, so this one here, well, you know, if you look at the picture over there, it's telling you that you should really think of the two branches of the parabola meeting together at one point. And you know, the calculations involved here are really completely trivial. There's absolutely no thought about doing this calculation. I mean, you might get the coordinates wrong, but the calculations are completely trivial. You don't have to think about points at infinity. All you have to do is substitute x equals 1 or z equals 1 in the equations. Okay. So, does this guy, the word, as I said over there, conic, plane conic, these curves that I'm describing are conics in the plane. They're also called conic sections. They were studied by a guy, Apollonius of Perga, about 200 BC. And his picture of them is this. His picture of them is this. Let's take a round cone. Right, so you know, this might, for example, be x squared plus y squared equals z squared. Right, then at each level of z, I've just got an ordinary circle. I've got x squared plus y squared equals some positive constant. So at each level here, I've got a circle. This is just the cone over a circle. Yeah? And what this guy said is, let's take this picture and cut it by a plane. So I cut it by a plane that looks like this. I see an ellipse. I cut it by a plane that looks like this. And I see, whoops, I see a hyperbola. Right? Or if I'm clever, I can also make a, how do you make a parabola out of this? If I take a plane which is parallel to one of the generating lines of the cone. Right, so I'm going to, so let's fix on this generating line of the cone, and then let's take a plane here which is parallel to it. Right? Because it's parallel to it, it cuts that part of the cone, but it doesn't cut the cone down there. Right? And this is, as you can see, if I was going from the ellipse, rotating my plane to get the hyperbola, then somewhere between the two I would get the parabola. Right? And so what Apollonius of Perga was doing 200 years ago was really projective geometry. So I don't really want to go into this, but projective geometry is geometry invariant under projection, and this is perspective geometry. So in Oriental languages, perspective geometry is called far near method. So you write, this is Matteo Ricci's translation, presumably. The building we're called in is named after Matteo Ricci. But perspective. And so this argument here, you take it, let's suppose that I've got a camera at this point, and I point it up there. I point it up there at the ellipse, right? Or I point it at the hyperbola, or I point it at the parabola. Then I see exactly the same thing. So if I'm taking a photograph of the ellipse, then the ellipse lies in this plane, and here's the photograph of it, and the thing that the camera sees is exactly this cone. Right? If I'm taking a picture of this hyperbola there and there, I look out with my camera, and what it sees is exactly the same cone. Right? So the three conics are in perspectivity from the origin. And this means they're projectively equivalent. Right? So I gave you this sort of coordinate description of the same result, but this guy, Apollonius of Perga, knew this perfectly well 2,200 years ago. The lectures at Sogang normally end on time. I'm sorry I went so late. I should have stopped 5 minutes earlier. So as I said, I'm very happy to answer questions or talk to people. Possibly some of you are embarrassed to ask questions in front of a large audience. But if you want to ask questions, catch me individually or send me an email.